The following concept is one that works both for regression and classification, so in this video we'll explain it using a classification problem. But as you'll see, all the arguments here work with regression algorithms as well. The concept is called regularization. It's a very useful technique to improve our models and make sure they don't overfit. So let's look at some data. Here's the data. And let's make two copies of it. And let's look at two models that classify this data. The first one is a line, and the second one is a higher degree polynomial curve. So the question is, which one is better? Well, they both have their pros and cons, right? The one on the left makes a couple of mistakes. As you can see, there is a red point and a blue point in the wrong sides, but it is much simpler. And the one on the right makes zero mistakes, but it's actually a bit more complicated. So let's say we want the one on the left because the one on the right overfits and it just doesn't generalize well. So the problem is that when we train the model, the one on the right will appear more likely, and the reason is the following. When we're training the model takes an error and minimizes it. So the model on the left has a small error since it only misclassifies 2 points, but it's an error nonetheless. The model on the right has a really small error since it does not misclassify any of the points. So if we train a model to minimize error, it will build a boundary like the one on the right, not the one on the left. So the question is, how do we pick the one on the left? Well, here's an idea. Let's look at the equation. So let's say the equation of the line on the left is something like 3x1 plus 4x2 plus 5 equals 0. And the equation of the polynomial is something more complex with higher degree terms like x1 squared, x1, x2, x2 cubed, etc. If we look at the equation on the left, it's much simpler than the equation on the right. In particular, there are less coefficients, only 3, 4, 5, whereas the right one has many more. So if we find a way to increment the error by some function of these numbers, that would be very helpful because in some way, the complexity of the model will be added into the error. So a complex model will have a larger error than a simple model. So let's do that, and I'll show you the details later, but the idea is that we take this 3 and 4, and notice that we're forgetting about the constant term, and there's a reason for that. But if we take this 3 and 4 and say add them to the error, we get a slightly bigger error. But what if we take all these coefficients and add them to the error here? Now we get a huge error. And now we can see that the model in the left is better because it has a smaller combined error. So again, what we did is we took the complexity of the model into account when we calculated the error, and in that way, a simpler model has an edge over the complicated model. And simpler models have a tendency to generalize better, so that's what we want. So now let me be more detailed on how to take the complexity of a model and turn it into part of the error. In summary, we'll take these highlighted coefficients and somehow add them to the error. This method is called L1 regularization and is very simple. Here's how it works. What L1 regularization does, it takes the coefficient and just adds the absolute values of them to the error. So in this case, we're adding absolute value of 2, which is 2, plus absolute value of minus 2, which is 2 again, etc. And we see that they add to 21. In the linear case, we see that what we're adding is the absolute value of 3 and 4, which is 7. So as 7 is much less than 21, we can see that the complicated model gives us a much higher error. That's L1 regularization, and the 1 is attached to the absolute value. L2 regularization is very similar, and what we do here is instead of adding the absolute values, we add the squares of the coefficients. So for the complicated case, we get 2 squared plus minus 2 squared, etc., which gives us 85. And for the linear case, we get 3 squared plus 4 squared, which is 25, which is much smaller than 85. So again, we see that the complex model gets punished a lot more than the simple model. But now the question is, what if we punish the complicated model too little? Or what if we punish it too much? Maybe some models, like a model to send a rocket to the moon or a medical model, have very little room for error, and we're okay with some complexity. Or maybe other models, like a video recommendation model or a model recommending potential friends or a social network, have more room for experimenting and need to be simpler and faster to run on big data, so we're okay with having some errors. So it seems that for every case, we have to tune how much we want to punish complexity in each model. This can be fixed with a parameter, and this parameter is called lambda. What we do with lambda is we multiply the complexity part of the error as follows. Let's look at the two models again, and let's remember that the yellow part of the error comes from the misclassified points, and the green part comes from the complexity of the model, namely the coefficients in the polynomials. Let's say we have a small lambda, so we take the green error and multiply it by a small lambda, which gives us something small. Therefore, the right model still wins because the complexity part of the error is small and it won't swing the balance. But if we have a large value for lambda, then we're multiplying the complexity part of the error by a lot, which punishes the complex model more, and then the simple model wins. So in summary, this is what happens. If we have a large lambda, then we're punishing complexity by a large amount, and we're picking a simple model. Whereas if we have a small lambda, then we're punishing complexity by a small amount, so we're okay with having more complex models. Now the question is which one to use, L1 or L2 regularization? So here's a cheat sheet with some benefits for each one. L1 regularization is actually computationally inefficient, even though it seems simpler because it has no squares. But actually those absolute values are hard to differentiate. Whereas in L2 regularization, squares have very nice derivatives, so these are easy to deal with computationally. The only times where L1 regularization is faster than L2 regularization is when the data is sparse. So let's say if you have 1,000 columns of data but only 10 are relevant and the rest are mostly zeros, then L1 is faster. L2 is better for non-sparse outputs, which is when the data is more equally distributed among the columns. L1 has one huge benefit, which is that it gives us feature selection. So let's say we have, again, data in 1,000 columns, but really only 10 of them matters and the rest are mostly noise. So L1 will detect this and will make the irrelevant columns into zeros. L2, on the other hand, won't do this. It will just take the columns and treat them similarly. So that's it. That's regularization.